Here is an example to recap permutation and combination and the relation between them. So here the top figure shows permutations, and here we have, you could think of it as different buckets. There is a bucket marked 1, there is a bucket marked 2, there is a bucket marked 3, there is a bucket marked 4. And now what we are doing is we are going to put balls in this bucket without replacement, but it matters what we put in the first bucket and what we put in the second bucket. And that's what we mean by the order matters. So in this case, we have the same set of balls put in different order. And in this example, so here this ball, instead of it being in 1, it's in 2. This, instead of it being in 4, it's in 3, etc. But it's the same color, same set of colored balls that we have. But in case of permutations, these are different arrangements, and therefore in permutation order matters. In combination, we are looking at all of this as one set, and therefore the order doesn't matter. So these two organizations are basically same as far as selection is concerned because they have the same set of balls. Next, look at the relation between CNR and PNR. The first observation in this case we have is the relation between PNR and CNR, which is PNR is C of NR times P of RR. So let's see why this is true. This is an instance of the product rule that we saw earlier. So what does this say? This says I'm supposed to put R elements in order out of the n elements. So I have arranged R elements in order. So what I'm going to do is I'm going to do this in two steps. First step, I'm going to select the R elements. And then I'm going to arrange them in some order. So how many ways can I select the R elements? Well, the number of ways I can select the R elements is exactly C and R. Now once I select the elements, I can arrange them in different orders. So here I have only R elements to begin with because already the selection has been made. And I have to put these R elements in any order that I like. And that means this is P of R comma R because I have R objects. I need to arrange those R objects in some order. So this is exactly what I have in the text on the slide as well. We have to first select R objects out of the N objects and then arrange them in some order. And so by the application of the product rule, we can see that we have P of NR is C of NR times P of RR. Let's look at the second example, second observation. Here we are going to relate C of NR to C of N minus 1 comma something. So here I have N objects out of which I'm supposed to select R, and the order does not matter. So what I'm going to do is I had this N objects. Out of this N objects, I'm going to call one of the objects as red. Now I can decide whether to have this object or not, If I have this object, that's going to give me one set of combinations. If I don't have this object, I'm going to get some other set of combinations, and the combinations that I want are ones where either this object is included or this object is not included. So let's suppose I include this object. That means out of this remaining, I have to select r minus 1. So that means I have n minus 1 objects, and I should select r minus 1 out of it. So that's going to be one possibility. The second possibility is we do not choose this object, and now I am forced to select all the r objects out of these remaining. So I have n minus 1 objects at this point, and I should select all r out of it. So that's how I'm going to get two different possibilities, and each of the possibilities is something that I need to consider. So by the sum rule, I'm going to get this observation that C of nr is C of n minus 1 comma r minus 1 plus C of n minus 1 comma r. So this is the same thing in text. So let's say there is one object, let's call it the red object. Now we need to consider two cases based on whether the object is included or not included. If we include the object, then we have n minus 1 objects, and we have to select the remaining r minus 1 out of it. And if I don't select that red object, I'm left with n minus 1 objects, and I should select all r out of it. The next observation is to compute r permutations. One observation here we have is P of nn. That means I have n objects and I need to arrange all n objects in some order. Is going to be n factorial. We can prove this by induction on n. So the basis is when n is equal to 1. If I have one object, I need to arrange it in some order. There is exactly one way to do it, which is the same as 1 factorial. So we are going to assume that this is true for some value n minus 1. So let's assume that P of n minus 1 comma n minus 1 is n minus 1 factorial. That means if I have n minus 1 objects and I need to arrange all of them in order, in some order, then we can do that in n minus 1 factorial ways. So now we have to look at what happens if we add one more object. So we have n objects. So we are going to use this observation over here to compute P of nn. So to arrange n objects in order, we first single out one of the objects, then we arrange all the remaining n minus 1 objects, and then we put the nth object somewhere in that order. So let's say if I had this as my ordering of n minus 1 objects, the object that I kept aside, where can I put it? I can put it either here, I can put it 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 here. So if I had started with n minus 1 objects, then there are n different ways that I can do this. So that means P of nn is going to be n times P of n minus 1 comma n minus 1. And by induction, we know that this value is n minus 1 factorial. We plug that in, and that will give us the answer that we want. Our next observation is P of n comma r is n times n minus 1 times n minus 2 all the way up to n minus r minus 1, which we can also write as n factorial divided by n minus r factorial. The proof is as follows. So if we have r objects to select, so we can think of this as having r buckets. The first object we can put in n different ways because First object can be any of the objects that we have. Since replacement is not allowed, we cannot reuse the same object. The second can only be filled with n minus 1 possible ways, and so on and so forth until the last one that can be filled with n minus r minus 1 ways. And this is basically same as, if I look at this, then I can multiply it by the remaining terms from n minus r all the way up to 1 and divide by the same, and that will give us n factorial divided by n minus r factorial. Now, couple slides ago we proved that P of nr is C of nr times P of rr. We have a formula for P of nr, so we can plug that in and we can see that C of nr is n factorial divided by r factorial times n minus r factorial. An observation from here is C of nr is same as C of n comma n minus r. And this is expected because when we select a group of R objects, we're also selecting a group of n minus R objects, which is whatever is left. And so there are a certain number of ways we could select R objects. We can select n minus R objects in exactly the same number of ways. Once again, we have reached the check before go ahead slide. I wanted to remember the formula for CNR and PNR. I want you also to understand how we got the sum and product rule to find the value of CNR and PNR. In particular, we use the product rule for finding PNR, and we use the sum and product rule for CNR.